What would make you abandon your home forever? Not just move cities, not just change countries. Abandon the entire element you're designed for. Around 375 million years ago, fish did exactly that. They left water, the medium that had sustained vertebrate life since its origin, and dragged themselves onto land. With lungs that barely worked, with fins that weren't meant to walk, into air that dried their skin and gravity that crushed their bodies. Why would evolution favor such an obviously suicidal move? The answer isn't what you think. For 400 million years, vertebrates ruled the oceans but never dared leave them. Then a few desperate fish in drying pools evolved the most revolutionary adaptation in animal history. Legs. This is the story of our ancestors' first steps on land. By the end of this episode, you'll understand how fish became tetrapods, why leaving water was actually a survival strategy rather than exploration, and how a series of environmental disasters created the exact conditions needed for the most important transition in vertebrate history. This isn't a story about progress. It's a story about desperation creating innovation. How do you evolve legs when you don't know what walking is? Devonian period 385 million years ago. The continents are green now. Forests of early plants and tree-like ferns. Deep soil, abundant insect life. And water is everywhere, but it's unstable. The climate swings between wet and dry seasons. Rivers flood, then dwindle to isolated pools. Swamps expand and contract with rainfall. In the oceans, fish have diversified into thousands of species. They have jaws now, bony skeletons, sophisticated senses. They're the apex predators of their world. But in the shallow freshwater environments, rivers, swamps, seasonal pools, there's a problem: overcrowding. Did you know that shallow freshwater environments, while rich in nutrients, are incredibly unstable compared to oceans? Temperature fluctuates wildly. Oxygen levels drop when algae blooms die and decompose. Pools dry up completely during droughts. Fish living in these environments face constant crisis, and crisis creates selection pressure. The fish that could tolerate low oxygen survived longer. The fish that could survive brief exposure to air lasted through pool evaporations. The fish that could move between pools when one dried up had access to resources others didn't. These weren't advantages in normal times. They were survival tools for disasters, and disasters were becoming frequent. Let's talk about a specific group of fish: lobe-finned fishes. They looked like typical fish: streamlined bodies, scales, fins. But their fins were different. Most fish have ray fins, thin membranes supported by flexible rays. Great for swimming, useless for anything else. Lobe-finned fish had fleshy fins with bones inside. A single bone connecting to two bones connecting to many small bones. Sound familiar? It should. That's the same pattern as your arm. One humerus, two forearm bones, radius and ulna, many wrist and finger bones. But these fish weren't using fins for walking. They were using them to push through dense underwater vegetation and prop themselves up on river bottoms. Why would a swimming animal need to prop itself up? Because in shallow, murky swamps, the bottom is where food is. Detritus invertebrates, hiding prey. Fins that could support weight gave access to food sources other fish couldn't reach. That's the first innovation: weight-bearing fins, not for land, for better access to underwater resources. The second innovation was lungs. Did you know that many ancient fish had lungs long before any fish walked on land? Lungs didn't evolve for terrestrial life. They evolved for low-oxygen water. When water is stagnant or choked with decaying vegetation, oxygen levels crash. Gills can't extract enough, but the air above the water has plenty of oxygen. Fish that could gulp air and absorb oxygen through vascularized tissue in their throat or primitive lungs survived when others suffocated. These fish would swim to the surface, gulp air, then dive back down. Still fully aquatic, still fish, but capable of breathing air temporarily. Now combine those two traits: weight-bearing fins and air-breathing lungs. You have a fish that can survive in the worst freshwater environments. Oxygen-depleted pools with dense vegetation. These fish were specialized survivors, not ambitious pioneers. How does a survival adaptation become a revolution? Around 375 million years ago, something changed. The climate became more extreme. Wet seasons shorter, dry seasons longer. Pools that usually refilled after a few weeks started taking months to refill, or didn't refill at all. For most fish, this meant death. But for lobe-finned fish with lungs, it meant opportunity, if they could reach the next pool. Here's the problem. Traveling overland is nothing like swimming. Water supports your body, air doesn't. Gravity crushes you. Water keeps your skin moist. Air dries it out. Without moisture, gas exchange through skin stops. Water is everywhere around you. Air requires you to find it. A fish flopping on land dies within minutes, unless it has mutations that help. Even slightly thicker skin that resists drying, slightly stronger fins that can prop the body up, more efficient lungs that extract more oxygen from air. None of these are enough alone, but together, and an hour might be enough to reach the next pool. Did you know that modern lungfish can survive for months in dried mud by breathing air and slowing their metabolism? This is what evolution selected for, not walking but enduring. The fish that could endure longer traveled farther, found more pools, survived more droughts. Their descendants inherited slightly stronger fins, slightly better lungs, slightly more resistant skin. Generation after generation, the selection pressure intensified. The truly revolutionary fossils appear around 375 million years ago. Tiktaalik, a fish with a neck, with a flat head and eyes on top, like a crocodile, with fins containing a shoulder, elbow, and wrist. It still had scales, gills, a fishtail, but it could do something no fish before it could do. It could perform a push-up. Using its front fins, it could lift its head and chest off the ground. Not walking, not even crawling, just pushing up. Why does that matter? Because lifting your chest allows your lungs to expand. Breathing air on land requires different mechanics than breathing underwater. Tiktaalik was at the threshold. Still mostly aquatic, still primarily a fish, but capable of crossing land when necessary. How long before when necessary becomes all the time? By 365 million years ago, true tetrapods appeared. Acanthostega, Ichthyostega. These weren't fish anymore. They had 4 weight-bearing limbs with digits, fingers, and toes. They had ribs that could support their body weight in air. They had stronger necks. But here's the twist. They were still aquatic. Did you know that early tetrapods were probably worse at moving on land than Tiktaalik? Acanthostega had 8 fingers on each hand, weak wrists. A tail built for swimming, not balance. These weren't land animals. They were swamp dwellers that could breathe air and haul themselves through shallow water and mud. So why develop legs at all? The prevailing theory used to be to walk on land, but the evidence suggests something else: to navigate complex underwater environments. Swamps aren't open water. They're mazes of vegetation, fallen logs, roots, and mud. Swimming through that is hard. Walking through it, even underwater, is easier. Legs gave tetrapods the ability to push through dense swamps, climb over obstacles, and move through water too shallow to swim in. They were swamp walkers, not land walkers. But there's a problem with being a swamp specialist. What if the swamps dry up? Because that's exactly what happened. The late Devonian was a period of repeated environmental stress. Climate instability, mass extinction events, massive die-offs of marine life. Freshwater environments weren't spared. Droughts intensified. Swamps shrank. The specialized swamp-walking tetrapods faced a choice: adapt to drier conditions or die. What if legs, originally evolved for swamps, turned out to be just good enough for land? By 360 million years ago, the first truly terrestrial tetrapods appeared. They were small, salamander-like, vulnerable, but they could walk on land. Not well, but adequately. They could breathe air continuously, not just in emergencies. And they could exploit a resource no vertebrate had ever accessed: terrestrial insects. The forests were full of them. Millipedes the size of your arm. Primitive insects everywhere, spiders, scorpions, all of that protein. None of it defended against vertebrate predators because vertebrate predators didn't exist on land yet. Did you know that early land tetrapods probably fed almost exclusively on arthropods? This was a food bonanza. In water, you compete with thousands of other fish species for every meal. On land, you're the only vertebrate predator in the entire ecosystem. The selection pressure flipped. Instead of "can you survive on land," it became "can you exploit land better than your competitors?" Tetrapods that could move faster caught more prey. Tetrapods that could venture farther from water accessed more territory. Tetrapods that could tolerate drier air expanded into more habitats. Within a few million years, tetrapods diversified. Some remained tied to water, reproducing in pools like their ancestors. Others pushed further inland, developing adaptations for more terrestrial life. Stronger limbs, better lung efficiency, skin that resisted water loss more effectively. By the end of the Devonian, around 359 million years ago, tetrapods were established as a permanent part of terrestrial ecosystems. Not dominant, not even particularly diverse, but present. Surviving, evolving. Why does this matter for the story of life? Because every land vertebrate that has ever existed, every amphibian, reptile, bird, and mammal, descends from these early tetrapods. Your hands have 5 fingers because early tetrapods settled on 5 as the optimal number through trial and error. Early species had 7, 8, even more digits, but 5 worked best for the kinds of movement terrestrial life required. Your spine has the structure it does because tetrapod ancestors needed to support their body weight against gravity. Your breathing mechanics, expanding your chest with ribs and diaphragm, trace back to the first tetrapods that needed to pull air into lungs without water's buoyancy. Did you know that the hiccup reflex exists because your ancestors were fish that breathed through gills and lungs simultaneously? Evolution doesn't erase the past, it builds on it. Every human being is a modified fish, a fish that learned to walk. Tetrapods were on land. They had claimed a new frontier, but they were still prisoners of water in one crucial way: reproduction. Every single early tetrapod had to return to water to breed. Their eggs had no shells. Their larvae had gills. Their entire reproductive cycle was aquatic. You could walk on land, hunt on land, live on land. But to create the next generation, you had to go back to the pools. This limited how far inland tetrapods could venture. They were tethered to coastlines, rivers, and swamps. To truly conquer land, to break free from water entirely, tetrapods needed to solve the reproduction problem. They needed eggs that could survive on land, development that didn't require water, young that could breathe air from birth. That innovation was coming, and when it arrived, it would change everything. What happens when animals no longer need to return to water? When reproduction itself becomes terrestrial? Next episode: the oxygen surge. How plants flooded the atmosphere with oxygen, creating conditions that allowed insects and tetrapods to grow to impossible sizes, and setting the stage for the age of amphibians. Subscribe to explore more. This is HistoPrimordia, where history comes alive. Thanks for watching. Subscribe now and join us for the next episode story.